on digital signal processing. And first, I like to give the brief overview of the MATLAB software. Already, you have got some idea about the MATLAB software, how to do the MATLAB based program in script or the live script, as well as in the Simulink. And after that, I will give the brief idea of the fundamental of the digital signal processing, digital filters, LTI system, the stability analysis of LTI systems, and a brief idea on the code generations and hardware implementations. Okay. So what is digital signal processing? So in brief, I can tell you that there is two part. One is the signal, another is the processing. Okay. So here I can say that digital signal processing is all about manipulating and analyzing the signals using digital means. There are two types of signal. One is the analog signal, another is called the digital signal. So in case of DSP, basically we are analyzing the signal using the digital methods, and typically with computers or special processors, we basically solve that kind of task. Okay. So here you can see that from that image you can see that this is a example of the recording of music. And in that case some background noise may be there. Okay, so must be some technique to eradicate the noise, to remove the noise, and to get the noise free audio. Okay, so there should be the music clearer, which basically remove the noise from the background. So this is the one example. Or that kind of audio or the music that can be generated, which usually can be compressed. I mean the file size may be compressed. It may be the 2 MB or 1 MB for less storage space. Okay, so here I have write these bullet points. That first is the processing of analog signals in the digital domain. That is the first thing in case of digital signal processing. Also input and output of the analog signals will be there, because here you can see that microphone, the signal conditioner. So here microphone is the input, and after that the intermediate stage you can find some components like signal conditioner, anti-aliasing filter, A to D converter, that is called the analog to digital converter. And after that the digital signal can be processed to the DSP processor, and which can be processed in the binary form. And after that, again, to get the analog signal, the DA converter, means digital to analog converter, is required. And to get the noise free signal, or we have to filtrate the signal. So smoothening is required by using the filter. So this is uh, basically the parts of the digital signal processing. So in case of voice signal also, there should be some transducer. You know, the transducer is basically called as a device which basically convert any kind of physical signal into the electrical form or the electronic form. And after that, this electronic signal can be processed through the electronic processor. There should be the transmitter is there, and after that we get the waveform. So here you can see that already I have told you that there are terms are there. That is, the one is the digital signal, and that is called the processing. So digital signal is basically the signals which are represented by a series of numbers. Okay, already I have told you that that can be represented in a binary format, and it is actually opposite to the analog signals, which are basically in the continuous type. Why it is done? Uh, Okay. Next is the processing. Processing is basically it involves the applying of mathematical algorithm. All yeah, yeah, in yesterday's session and day before yesterday's session, I think Shalu madam was there, and he actually discussed about the statistics and machine learning part. Okay, so there are different types of algorithm. You can develop that kind of mathematical algorithm or machine learning algorithm which can be used for getting the predictive model or the specific outcome for a particular signal. Because if you can consider a signal, so this signal having a particular frequency or the amplitude, and from that signal we have to get the we have to get some data. We have to get some data, or also there should be the stages like pre-processing stage will be there, and after that, after pre-processing, you can apply some algorithm or the model to get the uh, proper outcome. So this is the two part, that is the one is the digital signal, another is called the processing. So where DSP can be used, DSP can be used in case of audio processing for making the noise music better. Okay, for music compressions, noise cancellations or the noise removal, or in case of speech recognitions or voice recognition system. Next is the image processing part. Image processing, I think tomorrow the speaker will discuss on the image processing part. So where any kind of image that maybe it may be the RGB or true color image, or maybe the binary or grayscale image. So we should process we should process the image, or from that image we should get it is required to get the meaningful insights. Okay, we can use some filters. We can use some filters. We can sharp the photos, or we can if it is a blur conditions, we can unblur the photo. Okay, so and other type of steps are there, like in case of morphological processing um, or image sharpening. So there are different types of techniques are there that will be discussed tomorrow. So in case of image processing, DSP can be used, or also for communications part, like for transmission, for transmitting a signal from one end to another. So at that point of time, there should be different types of modulations techniques are required. We have to compress the data for transmissions over network, and also error corrections is required. And also in case of control system, their DSP can be used. So this is one challenge. This is one case study, or you can say it as a user story. So this is about the ambulatory ECG sensing. So what is about the ambulatory ECG sensing? So ambulatory ECG sensing is basically the non-invasive method of monitoring person's heart rhythm over an extended period of time. Okay, so here, unlike traditional ECGs, which provide a snapshot of heart activity. So here, in case of ambulatory ECG, it actually offered the continuous monitoring and allowing the detections of irregular heartbeats. So MATLAB will play a very vital role. MATLAB already you know that MATLAB has the dedicated toolbox. So there are 123 or 124 number of toolboxes. So if the challenge is to design and implement an embedded system for extracting accurate informations from the noisy electrocardiogram signals, so there should be some solutions to remove the in-band noise. So there are some toolbox is there, app is there, like fixed point designer app, or the fixed point designer app that actually help to remove that kind of noise. And also if you want to deploy it for a hardware based applications, you can use some microcontroller like SoC or FPGA based microcontroller, or ARM Cortex M series processor. So there is a some hardware package is there. You can install that kind of hardware package, and you can deploy you can deploy the C++ or HDL code to that kind of processor. I think it is clear to you. So if the challenge is like that way, so, to remove that kind of noise, so some toolboxes is there, some apps is there that actually help you to remove that kind of noise, and after that you can deploy it for the hardware-based applications. And finally, eventually, you will find that the result. Okay, so where you can find that power and the memory consumption will be minimized, or development accelerated by 300%. So that kind of thing we will discuss in later. Okay, so but before that I am giving you the quick idea of the MATLAB software. So MATLAB is already, I have told you why MATLAB is very much useful, because MATLAB, the full form of MATLAB is matrix laboratory. Okay, so if I consider image, so image is a form of matrix, so that will be represented in a pixel format. Okay, so pixel is called the picture elements. So so while we are considering the digital signal processing, or maybe the digital image processing, so while we create a matrix, or a matrix as a filter, and we apply that filter on a particular matrix, particular matrix, using some convolutions method, we can get some feature map. Okay, so for this kind of advantage, basically the engineers and scientists, they are using MATLAB. Next, from the previous challenge, already I have discussed on the high level language, because MATLAB has the capability to generate C++, or VHDL code, like very high definition language code. So if you want to deploy your code to the hardware based applications, it can be possible. Okay. Next is the IDE. IDE stands for Interactive Development Environment. It is very user friendly, and you can find, yes, not only you will find that kind of script based application, it is possible. Also, you can get the proper visualizations, you can get the yeah, you can get the UI, that is called the user interface. Okay, for the particular applications. Okay, so this kind of advantage, or this kind of facilities you will get from here. These are the basically the key features, and especially for signal processing, for the data analytics is required, deep learning is required, or maybe the machine learning signal processing. These toolboxes are required. Okay, so these are basically the main toolboxes which is basically helpful for the digital signal processing. And also you can see that there are interactive apps which can help you to automatically generate the programs. Okay, so next thing is the technical computing workflow. So what is mainly the technical computing workflow? Uh, in case of while you are dealing with any kind of data, it may be the text data. Okay, so while you are dealing with some machine learning algorithm at very previous stage, you have to deal with some uh, data. Okay, so it may be the audio data, it may be the video data, it may be text data, it may be that data may be in the HTML format, or maybe the XML format. So you have to access the files in the different form. Okay, also you can get some data from the softwares, or you can get some data from the web repository. Okay, so that kind of if you want to handle any kind of challenge on the speech processing, at that point of time you can get the signals from the web, and after that you can apply some algorithm or mathematical model on that mm, signal. Okay, next another is the hardware and scientific instruments. Hardware means, suppose already I have told you that ARM Cortex controller, or maybe the Raspberry Pi, Arduino, or the FPGA. So that is something is the Xilinx Altera board. So these are basically the hardwares. Also some sensors which are also responsible to get the physical data. Like suppose I want to capture the temperature or the humidity or maybe the audio data, so by using mic, so that kind of sensor microcontroller interface create a hardware system. Also some scientific instrument that is also responsible to generate some signal. So these are basically help to for the data acquisition process, help in data acquisitions process. Next is the in case of intermediate stage, you will find some analysis part. Okay, so here you can apply some mathematical algorithm or some functions, some inbuilt functions, or maybe some user defined functions that you can apply, and after that you will get a particular model or particular outcome. So in case here you can see that the signal processing is in the intermediate stage for analyzing or create the prototype or the model from here. And after that you can deploy the your code. It may be the C++ code or other VHDL code into the embedded system. Also, you can generate the report or the documentation here. So this is basically the technical computing workflow of of MATLAB. Okay, so next is the here you can see that this is basically the current folder. From here you can access the files. I'm not going into detail. This is the workspace form. You can where you can explore the data that you can create or import from files. Okay, and next here you can see the command window. Command window is the space where you can enter the command at the command line that is indicated by the prompt sign. And next is the plotting. So different types of plotting can be possible. In case of signal processing, you will find the different types of plotting. Okay, so here that kind of plotting can be possible in MATLAB. Okay, so this is all over the MATLAB environment. Here you will find the what is the menu bar, what is toolbar. If you want to get the details of digital signal processing, or if you want to find out the relevant examples on digital signal processing, you can click on the help sections and you will get the relevant uh, documents. Okay, documents. And also here you can see that www.github.com mathworks teaching resources. So you can note down this link. So if you click on this website, you will find some teaching resources, especially for the students, where you will get some relevant examples on the basically for the Fourier analysis part. Okay, so there are different examples are there, but here you can see that for signal processing or for the other applications, so that kind of awesome example you will find from here. Okay, so if you click on it, so you will get the relevant informations from here. Okay, so here you can see that suppose complex Fourier analysis. So you can see the .mlx file that is called the MATLAB live script. Okay. Or next is the Fourier series, how to solve any kind of Fourier series. Okay. So that kind of detailing you will find from here. Okay. So these are available in the MathWorks teaching resources. So this is available in the GitHub platform. Okay. Okay. Next is the Simulink. I think you know about the Simulink. Simulink is basically called the basically a platform. This platform is basically helpful for model-based design and simulations. You can create any kind of dynamical system. And important thing is that you can build that model by using the block diagram based presentation. Okay, so here you will see that there are different types of blocks. You can fetch the block from the Simulink library browser. From the Simulink library browser, you can fetch the relevant block, especially for any kind of electrical or electronic systems, or maybe for the digital signal processing. So you can face that kind of blocks. So if you want to want to work with triangular waveform or the step signal or the ramp signal, so you can face the block from the sources. Or if you want to display any kind of signal or the outcome in the output, so at that time you have to use the scope. So in case of any other mathematical operations or computations like convolutions techniques or addition, subtraction, so that kind of mathematical blocks are available. So these are basically the Simulink, where you can do the simulations or the model based design in this platform. So this is the multi domain environment, and you can test that your system under all conditions, or also you can change your block parameter. So especially while you design any kind of model at initially, you can design a model. Okay. So like that way you can design a model. Okay. So this is your model. Okay. This is your model. So after that you can get up certain outcome, but your outcome is not your desired outcome, or you desired outcome. So at that time you can change the block parameter value. So these are basically these are basically the blocks. So these are called the blocks. So this is the block, this is the block. So these are basically blocks. So if you click on this, you can get the block parameter description, as well as you can change the value of this block parameter accordingly. So this can be done by using Simulink platform. Also, it will help to simulate the closed loop system behavior, and it will help you to test under all conditions. It is also help to test under all conditions in case of real-time conditions also, and it is also help to create the C code and HDL code, and you can deploy that code to the embedded processor and FPGA based system. Okay. Okay, so this is the concise uh, flowchart, or you can say that workflow, that if you have any kind of research problem or the requirement, so you can use that you can use that Simulink platform for design purposes. So here you will find some physical component. Basically, the physical component is available in Skinscape platform. Also, you apply your own algorithm, and you can create the system or the subsystem in the form of a block. Okay, you can write a script and you can form a block, and you can apply your own algorithm here. And after that, you can for microcontroller unit or DSP unit, you can generate the C++ code. For FPGA or ASIC based system, you can generate the VHDL or Verilog code, or for analog hardware, you can generate that kind of code. So this can be possible in Simulink and Simscape platform. So these are the toolboxes. Okay. So toolboxes is basically it is why it is important, because already our previous speaker has already discussed on different types of function scripts, but here some toolboxes, new toolboxes are there, which is basically introduced in the 2024 A version. Okay, so here you will find that the communication toolbox or the signal processing toolbox, though it is the old available in the old version of MATLAB, but here you will find every year MATLAB actually update that kind of toolbox, and every year you will find the new functions which can be introduced, or the existing functions which can be modified. Also, some extra features or the apps can be added in this toolbox package. Okay, so toolbox is basically a collections of functions that is built on the MATLAB technical computing environment. Okay, so here it is important thing, because after this session you have to know which toolboxes are very much important for your signal processing applications. There are different types of applications are there, like suppose anyone is enthusiastic in the robotics application, someone is interested in code generation, or statistics and optimizations. So there are different types of toolboxes are there for different applications. So in case of signal processing and wireless communications, you will find that these are the list of toolboxes. These are the list of toolboxes which are available for the signal processing and wireless communications. Among these toolbox, basically the audio toolbox, DSP system toolbox, sensor fusion and tracking toolbox, wavelet toolbox, signal processing toolbox, signal integrity toolbox. These toolboxes are very much important for the academic problems. Okay, and also for model based design, these list of toolboxes are helpful. We will not we will not discuss on the radar toolbox or the RF toolbox, but this toolbox will be helpful for you. Okay, so these are the new toolbox which is introduced, like Bluetooth toolbox or the DSP HDL toolbox or industrial communications toolbox. These are the new toolboxes which is introduced in the MATLAB 2024A or 23B. Okay, so this is very important. Okay, and yes, and after that, on ramp is there. If you go to the MathWorks website, you will see the signal processing on ramp. Here you will see the step by step process, like pre-processing, how to do the spectral analysis or the filtering or the signal measurement. So that kind of hands-on experience or the videos are available in the on ramp sections. Okay, and after course completions, you will be certified like that way. Okay, okay, so now I will discuss some example on the signal processing. So first is I will give you some quick demo on the how to generate the signals, how to design a digital filter in the live editor task, and the digital filter design in the app, and also I will discuss on the IIR and FIR filter response. Okay. So basically, as I am already told you that mm, DSP, that is called the Digital Signal Processing Toolbox, or the Signal Processing Toolbox, is very much important, because in this toolbox you will find the collection of tools or the functions which is expressed in the M files. M files stands for the MATLAB script file. Okay, so for implementing for handling different types of varieties types of signal processing tasks, this toolbox is very much important, because you have installed MATLAB software, but you don't have any signal processing toolbox or DSP toolbox. Then you can't handle any kind of example, though it is available in the MathWorks website. But while you try to run or try to simulate that kind of program or the model, at that point of time it will throw error that that package or that toolbox is not in your computer. So at first you should you should be aware of that toolbox. Okay, so and this toolbox is basically help to solve that kind of problems. Okay, that kind of problems, like how to design the analog filters or the digital filters, how you can generate the waveform, okay, or the statistical analysis of the signal processing or the spectral analysis. So that kind of thing you can do by using the signal processing toolbox. Okay, so first I will try to give you the demo on the generating signal, how to generate the signal. Okay, my screen is visible, sir. MATLAB screen is visible. Anyone please respond, my MATLAB screen is visible or not? Okay sir, okay sir, thank you so much, sir. So yes, so this is basically called MATLAB live script. If you go to the new section, here you will see that script, live script, function, live function, class, system object. So if you click on script, uh, here only one window will open, where you can write only the command. Okay, so that is represented by the command lines, different command lines. You can write only the line of codes. Okay, but live script is the uh, new feature of MATLAB, where you can add the text as well as the code. So this is the text section, this is the text section, and this is the code sections. So you can, if you go to the live script option, if you go to the live script or the live editor, so what is the beauty of live script of live editor, that you can add your text here, you can add images also while you are writing any command in the command line. Sorry, first of all, in this particular script, you can add text, add headlines, add different bullet points, or any descriptions of that problem, etc. Okay, next thing is that you can add images also, you can add equations also, you can add links. Okay, so there are different you can add different types of format here. Okay, next thing is that you can customize your text. So there is a different types of option. And next, here you can see that if you click on this thing, that is the code, so then it will be converted to the code section. Okay, it will convert to the code section. Okay, next is important, that task. Okay, so if you click on it, you can add different types of tasks, like suppose you want to pre-process any kind of data. Okay, suppose you are dealing with a signal, audio signal, or a data set which is created from a signal. Okay, data set which is created from a signal. So from that data set, from that data set, while you process the raw data, through this MATLAB platform. Okay, so it may not it may generate inaccurate outcome, because of the raw data. So pre-processing stage is required. Why pre-processing stage is required? Because here if the data is at unbalanced condition or noisy condition, so if there is any kind of missing values, so you can eradicate that kind of data. Okay, and it can balance the data, you can smooth the data by some interpolation techniques. Okay, so this is all can be done in the pre-processing stage. Now there are certain apps are there which can be directly added to that particular MLX platform. .mlx, because here you can see that it is called .mlx. .mlx is the MATLAB live script, and .m is the MATLAB script. Okay, so here you will find that kind of apps which can be easily added. Also, you can generate the code from here. Okay, next is the control. Suppose I want to change the variable value. Okay, suppose a equal to 5. Now I want to change the value. Okay, so at that time I can use the numeric slider. Okay, similarly I can use the button. Suppose I want to design an app, and I want to I want to click on the start button. So I want to if I want to create a start button, so then I can use that button sections, and under this button section you can customize the code. Okay, customize the code so that it can generate the outcome. Okay, so this is the beauty of live editor. Okay, now here in case of signal generation, I am undock this uh, editor. Okay, so this is the signal generation for signal generation and visualization. Okay, so this example basically shows how to generate widely used periodic and aperiodic waveform, or the sequences like impulse sequence or the step sequence or the ramp sequence. Okay, so and also through this example I will try to show you some multi-channel signals, some pulse trains, and uh, sync function or the Dirichlet functions which is available in the signal processing toolbox. Okay, okay, so here, okay, so here you can see that clear all, close all, and CLC. Clear all means clearing everything initially, whatever be your garbage files that can be easily cleared, easily cleared at initial. Okay, just a minute, hold on. Okay, just a minute, hold on. Okay, so clear all means clear is so if I open my MATLAB window, this is the MATLAB window. If you enter in the command line, if you type CLC, then CLC means it will clear all the commands from the command line. Okay, clear all means whatever be the variables appeared in the workspace, that will be cleared. Or if any kind of program that will be at running condition, if you will be at running conditions, that it will clear it. Okay, and close all means for all the previous programs or programs can be closed and it will start from initial. Okay, so in case of periodic waveform, so here t equal to 0.1 colon 0 10. Okay, so here this is the continuous waveform. So the sine wave is basically called the periodic waveform. Okay, so I am declaring the time 0 colon 0.1 colon 10. So this is basically the step size 0.1. So from 0 to 0 is the initial value, 10 is the final value. Okay, so 1 minute, just a minute. Yes, uh, one. I think it is clear right now. Okay, so t is equal to 0.1 colon 10. So 0 is the initial value, 10 is the final value, and 0.1 is the step size. So all the intermediate values between 0 and 10 can be created with the step 0.1. Okay, next, um, if I want to create the sine wave, so I have to use the sine function, that is sine within bracket t, then I can create the sine wave. Okay, now next is the plot t comma sine wave. I can create the sine wave function and x label for labeling the x-axis and y-axis. This is very easy because for labeling x-axis and y-axis I have to declare the string value within within this semicolon. Okay, within this inverted comma. Next, to keep the previous plot, we have to use the hold on function. Similarly, if I want to create the same signal, or if I want to plot the same plot another signal with the previous signal, then we have to use the hold on function. So within a particular figure, you can visualize the two waveform. One is the sine wave, another is the cos wave. Sine wave is represented by the blue color, and cos wave is represented by the red color. So what is the beauty of this live script, that you can get the instant outcome with the program. Okay, so here you can see that you can get the instant outcome with it. Okay, and this is represented by the legend sine and cosine. Okay, now next thing is that in addition with the sine and cos functions in MATLAB, the basically the toolbox, this toolbox basically offers the other functions that produce the periodic signal, such as sawtooth function. So this is basically the sawtooth periodic function. Okay, so this sawtooth function basically generates a sawtooth wave with the peaks of, here you can see that +1, +1 and -1, +1 and -1. Okay, so you can generate the sawtooth waveform by using the sawtooth function with the peaks of +-1 and with a period of 2 pi. Okay, so here in this program you can see that if I write the sampling frequency fs equal to 10 kilohertz. Okay, suppose 10 kilohertz is the, so fs equal to 10 000. This is called the sampling frequency. Now here the time is represented like that because we know that t is equal to 1 by f. So 0 colon 1 by fs colon 1.5. So where basically it will generate to generate 1.5 seconds of 50 hertz sawtooth waveform with a sampling rate of 10 kilohertz. So we have to declare the lower bound as 0 and to generate 1.5 seconds. So 1.5 second is the upper bound. Okay, so 0 and 1.5. Okay, and 1 by fs is basically the sampling time. Okay, fs is the sampling frequency and 1 by fs is the sampling time. Okay, now x1 is basically the if I want to generate the sawtooth waveform, then I have to use the inbuilt function that is called the sawtooth function. Okay, so sawtooth is AWTWT sawtooth 2 pi ft. So 2 pi ft, f is considered as 50 hertz. So you can put the value directly 50 here, or if you type here f equal to 50, then you have to assign the variable f equal to 50. Okay, at initial. Next, if you want to generate any square waveform, then you can write the square 2 pi f 50t. Next, subplot. Why subplot? Because here 2 comma 1 comma 1, this is called the position of the plotting. Okay, 2 comma 1 comma 1. So if I consider one whole plot, so in 1 comma 1 position, in 1 comma 1 position, sawtooth periodic waveform can be seen, and in 2 comma 1 comma 2, the square periodic waveform can be seen. So I think from here you can see that this is the if I consider it as a matrix. Okay, so 2 comma 1 comma 1, so 1 position you can see the sawtooth waveform. So this is the one plot. So in this plot there is two subplot. Here it is one, this is another one. Okay, so you can plot t comma x1, and after that you can see that one. Okay, similarly you can create the aperiodic waveform. So if you want to generate any aperiodic waveform, it is also can be possible by using the tripulse function. Okay, tripulse function. So a tripulse function basically generates a sampled aperiodic waveform with unity height of triangular pulse, that is t equal to 0 with a default width of 1. Okay, default width of 1. Similarly, rect pulse. So this rect pulse function is basically generate the sampled aperiodic function with unity generate rectangular pulse center about 2 equal to 0 with a default width of 1. So here you can see this is fs is basically the sample frequency. Here you can see the sample rate of 10 kilohertz. So this is basically the sample frequency, and t equal to -1 by fs colon 1. Okay, I will share this program with sir, and I think this program will be easily accessible from your end. Okay, so next is the tripulse. So here you can see the tripulse. If you put here the tripulse function, okay, so then you can see the triangular aperiodic pulse. Okay, triangular aperiodic pulse. This is the triangular aperiodic pulse, and this is the rectangular aperiodic pulse. Okay, So like that way you can create a periodic waveform as well as the aperiodic waveform. Okay. Similarly, here you can see that if you want to generate any Gaussian, I mean the Gaussian modulated sinusoidal pulse. So this is 1 minute. Yes. So here you can see that this is the Gaussian pulse. Okay, Gaussian pulse. Okay, so basically the GA Gauss pulse. This is called the Gauss pulse. Is basically the function, inbuilt function that actually generates the Gaussian modulated sinusoidal pulse with a specified time. Okay, so here in the x-axis you can see the time is represented by the millisecond, and here you can see the amplitude. Okay, so this Gauss pulse is basically the function which basically generates the Gaussian modulated pulse. Okay, and he will find the center frequency and as well as the fractional bandwidth. Okay, so similarly, sync function is also there. Sync function basically helps to compute the mathematical sync function for an input vector or the matrix. So here, lean space is basically create the linearly spaced vector. Lean space is the function which actually create the linearly spaced vector. So -5 to 5, you can create the linearly spaced vector between the -5 to 5. Okay. So after that, whatever be the values that is generated from here, so these vectors can be passed through the sync function. Okay, so already I have told you that this sync function is basically the basically compute the mathematical sync function for an matrix or for an input vector. Okay, and it is basically the continuous inverse Fourier transform of the rectangular pulse. Okay, pulse of width 2 pi. Okay, so here you can see you can create the sync function, and after that you can plot it. Subplot 2 comma 1 comma 1, and it is very easy. You can plot it, and after that x label, y label, and so on. So like that way you can create the sync function. I'm not going into detail that one. This is sweep frequency. Achha, okay. 1 minute. Sweep frequency. Plot. Okay. Linear chart. Okay. Yes, yes. So here another example is the sweep frequency waveform. 1 minute. Yes, yes, it is visible now. It is visible. Okay. Now here you can see signal processing toolbox. Signal processing toolbox also provides the function to generate sweep frequency waveform. And this sweep frequency waveform basically generate the linear chirp, which is basically represented by the chirp function, CHIRP, chirp function. Okay, so there are two optional parameters which basically specify the alternative sweep methods and initial phase in degrees. Okay, so here you can see suppose I want to generate the 2 second, okay, 2 second at the rate of 1 kilohertz sample rate. At the rate of 1 kilohertz sample rate. 1 kilohertz means if it is a 1 kilohertz, so sampling frequency is fs. If I consider as f equal to 1 kilohertz, then 1 by t is t is 0.001. So the step size will be the 0.001. Okay, so t1 equal to 0 colon 0.001 colon 2. Okay, next next is the char function. So char function here, it can create like that way, that here you can if I want to create the char function with crossover frequency 150 hertz at 1 second. Okay, so so here t1 comma 0.0 comma 1 comma 150. Okay, 1 comma 150. So here t1 is the time. Okay, t1 is the time, and after that here you can mention the other parameters value. So like that way you can create the linear chart. Okay, similarly you can create the quadratic chart also. Quadratic chart, so in case of quadratic chart you can like write like that way -2.00.001 comma colon 2. So like that way you can create the chart. So this is the way to create. I am not going into detail because this is almost similar. Okay, so you can create the quadratic chart, you can create the linear chart. Okay, and after that or the concave chart, and after that you can plot it here. So you can see the waveform here. So this is the linear chart, this is the quadratic chart, you can see from here. Okay, just a minute. Okay, so this is all about the generating signal. So if you want to generate the different types of signal, already I have discussed that how to generate the periodic waveform, how to generate 1 minute. Yes, so how to generate the periodic waveform. 1 minute. Yes. Uh, hmm. The periodic waveform or the aperiodic waveform, or maybe the sawtooth waveform. Okay, so or if you want to generate any smooth pulse, like yeah, then you can use the Gaussian pulse function for sinusoidal pulse. Okay, or maybe the sweep frequency response, like at that time you can use the char function. So these are basically the way to generate the different types of signals. Okay. So here you can see that how to represent the signals in a as a vector. Okay, so you can represent it in a like that way, x equal to 1, 2, 3. So these are basically represented the vectors, and after that, if you write the stem x, stem is basically used for the create the sampling sampled visualizations of that particular signal. Okay, so this is the way to create waveform generations. Okay, so there are different waveform generations like sinusoidal, cosinusoidal waveform, impulse waveform, rectangular waveform, sawtooth waveform. Okay, so tripulse is there, rect pulse is there. Okay, so these are basically the first process of signal generation. Okay, next is the sawtooth waveform. There is a dedicated inbuilt function that is a sawtooth waveform. Square for square, generate the square wave form. Then you can use the square wave function. Okay, or square function. Okay, similarly sync function is there. Okay, so this is all about waveform generations. Any questions, sir? Any question? Okay. Okay, next I will discuss on the Nyquist-Shannon sampling theorem. Okay, so here I am discussing on the Nyquist-Shannon sampling theorem. Okay, so basically why it is important that I am telling you, because first is the theorem. So this theorem basically states, here it is written that this theorem is basically states that an analog signal waveform may be uniquely reconstructed without error from samples taken at equal time intervals. So basically here the sample rate must be equal, and also sample rate means if I consider fs is basically the sampling frequency, it must be equal, or it must be greater. It must be greater than twice of the highest frequency component in the analog signal. Okay. So here throughout this experiment we will refer to the FN. FN stands for the Nyquist frequency. Nyquist frequency, and Fs is basically the basically your sampling frequency. Okay. So in this experiment, basically we will understand why this theorem, why this Nyquist-Shannon sampling theorem is important, and when we decide that we do not need any Nyquist or Shannon theorem for sampling. Okay. So initially here you can see that throughout this experiment we will how we, there are two process. One is the FN is the sampling Nyquist frequency, and F max is basically the maximum frequency present in the sampling time. Okay. So before we dive into the theorem, let us first create a signal. So here we try to create a signal here, okay, that we can experiment on. And here we will be using 1 kilohertz signal. 1 kilohertz is basically our sine wave signal, which is our test signal. This is basically our test signal. Okay. So 1 kilohertz. So this is our signal frequency. 1 kilohertz means 1000. So F equal to 1000. We can use the percentage sign for comment purposes. Okay. Next, to get base representation or visual representation of this wave, we are going to sample the 1 kilohertz signal at 50 kilohertz. Okay. So here you can see that Fs is equal to 40 into F. Okay, so here choosing the sampling frequency, which is basically the 10x of the signal frequency. Okay, 10 times of the signal frequency. Now T equal to 1 by Fs. Okay, T equal to 1 by Fs. Basically, Fs is the sampling frequency and T is the sampling period. Next, now I want to create the time vector. Okay, time vector. So here you can write the 0 colon. It is basically the sampling period, and this is the upper bound, 6 e to the power of -3. Okay. So if I reverse the signal frequency here, then we can get okay. Next, the length of the signal L is equal to 6 e to the power of 6 e to the power -3 divided by t plus 1. This is basically the length of the signal. Now, using this equation, x equal to sine omega t or 2 pi ft, okay, we can construct our time domain signal. So 2 pi ft, so this is the 2 pi ft. So here we can compute the signal length for fast Fourier transformation. FFT is basically called as the fast Fourier transformation. Okay. So here I can put the value of f and value of t. Okay. So after that we can get the time domain signal. Okay. Time domain original signal. So like that way I can create the original signal of sine wave. Okay. Next, here I want to compute the optimal signal length for FFT. Okay. So here I can use the FFT function. FFT is basically the fast Fourier transformations for computing FFT. Okay. So here I can apply the FFT function, and I can get the absolute value or the magnitude of FFT. Okay. So for getting the absolute value or the magnitude, you have to use the ABS. ABS is basically for the absolute value. So here you can use the FFT command or the FFT function, x comma n. Okay, and after that you can get the magnitude of A50. So y divided by L. L is basically the length. Here it is written that L is basically the length of the signal. Okay, length of the signal, and y is basically the A50. So y divided by L, you can get the magnitude of the A50. Okay, so here you can see, if I want to ignore the negative frequencies, okay, in negative frequencies, so here we can apply like that way, y magnitude 1 colon n by 2. Okay, so to ignoring the negative frequencies. Okay, now here if I want to create the frequency range. Okay, so this is how I can create the frequency range f equal to 0 colon n by 2 minus 1 fs by n. Okay, so like that way you can create the frequency domain of the original signal. Now there are some cases. There are some cases for the Nyquist waveform, Nyquist sampling theorem. Okay, so here you can see that Fs is equal to 4 into F. Fs is equal to 4 into F. So here basically we follow the Nyquist frequency signal and we sample our signal at maximum frequency, 4 times of the maximum frequency. We will sample our signal at maximum 4 frequency. So Fs is equal to 4 into F. Now sampling period is t is equal to 1 by Fs. This is my sampling period, and after that, while I get the sampling period, I can create the time vector here. So this is lower bound of the time vector, lower bound of t, and this is the upper bound of t, and this is the sampling time period. Okay, so like that way, here from here I can create the time vector. Okay, time vector. Okay, 0 colon 0 colon t colon 6 to the power minus 3. Okay, and from here you can get the length of the signal. So 6 to the power minus 3t plus 1. From here you can get the length of the signal, and then you can compute the optimal signal length for F50. So sine 2 pi ft. So sine 2 pi ft, you can put the value of f and t here, and after that you can compute the optimal signal for the F50. So this is the time domain signal that is sampled at 4 kilohertz. Okay, 4 kilohertz signal. So if you look to this graph, so here 1 plus 1 for this is basically like a triangular waveform. So if you look at this graph, you will notice that the time domain signal basically looks different from the original. So initially you can see that this is the original one, this is the original signal, but after that you can see that the time domain signal, while it is sampled at 4 kilohertz, you will see that it is different from the original one. Okay, and it is more or less same characteristics to the original waveform. While we create the time domain of the original signal, so at that time here I have sampled it, the time domain signal sampled at 4 kilohertz. So 4 kilohertz. So at that time you can see that this is the almost more or less same characteristics of the original signal. So this means that we are basically successful in sampling of our signal. So here you can see, that the peak at 1 plus 1 and the negative peak at minus 1. And here you can see that this is the magnitude. Okay, so here you can also see that while it is sampled at 4 kilohertz, you can see the magnitude that at plus 1 at minus 1, and it is at 4 kilohertz, so 10 to the power of minus 3. So here you can see, and here you can see the same thing. Okay, so like that way you can check the different case studies that while f is greater than 2 times of maximum frequency, or if the fs is 2 times of the less 2 times of the uh, fs is less than the 2 times of the maximum frequency. So these type of cases can be verified in case of sampling theorem, because throughout this experiment we basically find out the sampling rate that should be greater than or the twice of the highest frequency component of the analog signal. Similarly, in that case, you can see that in that case we can see also that we will sample our signals at 1.5 of f max, 1.5 of f max. So this is the sampling frequency. So 1.5 times of f max, so 1.5 into f. So now what is the sampling period? Sampling period is t is equal to 1 by fs. That is basically the sampling period. If I want to create the time vector here, so t equal to 0 colon t comma 6 to the power of minus 6. So what is the length of the signal? So this is the length of the signal. So 6 is equal to minus 3 divided by t plus of 1. So like that way we can get the length of the signal, wavelength of the signal. Next, if I want to compute the optimal signal length for this per FFT, so here x equal to sine 2 pi f into t. Next, here in this time domain signal, while this time domain signal is sampled while at 1.5 kilohertz, you will get that kind of waveform. Okay, so you will get that kind of waveform. So if you okay. So if you look at this curve basically the time domain signal looks nothing like original signal, but it is actually curvy wave. Okay, and the spike is at here. The spike is 0.55 is uh, 5. Yes, yes. Here you can see, if you follow this curve, so while I sample that frequency, so this is the time domain signal. First of all, this is the time domain signal at 1.5 kilohertz. So in case 2, here you can see fs less than 2 of f max. Okay, so less than 2 of f max. So if I consider 1.5, so it is less than 2 of f max. Okay, 1.5f. Okay, and after that we can get the time domain signal. Next, I can convert it into the frequency domain signal. Okay, time domain to frequency domain. Okay, so by using the fast Fourier transformation, I can compute the magnitude ignoring the negative frequencies, and finally we can get the frequency range, and finally we can visualize the waveform in the frequency domain. Okay, so one case is the fs greater than 2 of f max, and another is one the fx less than of 2 of f max. So in that case, you can see that 1.5 kilohertz, which is less than 2 of f max. Now, if you look at the plot, here you can see that this is the spike. This is the first spike. Okay, this is the first spike, and you will now see that the time domain signal basically smooth, but the spike is at 500 hertz, 0. Sorry, yes, 0. Yes, this is the first spike. So first spike is at almost 200, and here another big spike, which is the maximum spike, which is at 500 hertz. Okay, so like that way you can find out the frequency domain signal sampled at 1.5 kilohertz. Okay, I think you have understood that one. So this is the Nyquist sampling, uh, Shannon sampling theorem. So first, here you can create the time domain original signal. After that, you can convert it to the frequency domain original signal. Next, I apply the two case studies. One is the f is greater than 2 of f max, while f is greater than 2 of f max. Here I have considered f is equal f is the 4 times of f max. Okay, so it is greater than 2 of f max, and after that we can get the time domain signal as well as the frequency domain signal at 4 kilohertz. Similarly, at the next case, f is less than 2 of f max, here I can get the again the time domain signal at 1.5 kilohertz, which is less than the 2 of f max. And next, here you can see for frequency domain signal at 1.5 kilohertz, we can get the waveform. So like that way I can find out this waveform by using the Nyquist sampling theorem, Shannon sampling theorem. Okay, just a minute. Okay. So here, so in brief, I can tell you that yes, sampling. So sampling is basically here I can tell you that it is a process of picking signal informations at given instant, and sampling basically depends on the sampling frequency, that is called fs is the sampling frequency, and it must follow the theorem. Already I have told you that Nyquist theorem. So this Nyquist Shannon sampling theorem is basically important for this processing. Okay, and here the condition is f is greater than 2 of f max, or and uh, fn equal to that Nyquist frequency equal to 2 of f max. So this is the condition for sampling. Okay, okay. Next, next I will show you not convolution. 1 minute, how much time left? Okay, okay. I will move little faster. Yes. So this is first of all, yes, yes. Okay. So first is another example that is in MATLAB app. This is called the first of all not in, it is actually called the app designer. This is called the app designer. Okay, app designer, and here you can see the different components. Okay, like it is here you can see that uh, the from this component browser you can select the different types of components like slider bar, table, axis, drop down button, edit field. Okay, so these things you can add from this component library. Okay, so I think it is visible. I think it is visible. So here, 1 minute. Yes. So this is the knob. So you can drag and drop this knob. Okay. Drag and drop this knob. So you can create, already MATLAB has some apps. Okay. Apps, but you can create your own app. Okay. So you just delete it. Okay. You just delete it for now. So from here you can just create your own app by fetching the component from the component library. Okay, so this is the design view, but in background you can see the code view of it. Okay, you can see the code view of it. So this is basically how you can you can customize each component. Okay, customize each component, and you can write the code behind that. Okay, so in this this is the example of the modulation. Okay, just a minute, I want to run the program. This is basically the sampling demo. If you change the sampling rate, you can find the sampling of the signal. Okay, if you change the sampling rate, if you increase the sampling rate, then also the sampled waveform, uh, you will see the more sampled waveform. Just a minute. uh, so you can change. Just it is not opening now. Just just filter designer, filter design. Image processing. MATLAB itself is a heavy software, so that's why it is little slow. Okay, I let it be open. Okay, I will discuss the another example using some video. So this is basically the filter designer app. Okay, suppose if you want to create any low pass filter or high pass filter, or if you want to use some any design method like Butterworth filter. Okay, uh, for design any IIR filter or FIR filter, it can be possible by using the filter designer app. Okay, so here you can see, just you type here the filter designer in the command window. Okay, so if you type the filter designer, or you can go to the apps. Okay, because my app is not opening for now because it is taking some time. Okay, so if you go to the app section, either you can click on the filter designer app, or you can write the command at the command window, that is the okay. Now this is open. Okay, so this is my app. This is my app. Okay, so in this app, you can see that if you change the sampling rate here. Okay, if you change the sampling rate, then 1 minute. uh, so this is called, yes, this is called the numeric slider. I think this is visible. I think this is visible. So how it can be done? So already I have told you that from the component library, you can use the knob. This is the knob. You can change the knob. You can change the frequency by changing the knob. Okay, and also you can change the sampling rate. Okay, you can add the numeric slider from the component library, and you can display the waveform. So this is my if I consider the sine wave is my continuous waveform. so it can be sampled like that way. Okay, so if I change the sampling rate accordingly it will be changed. Okay, so like that way you can change the sampling rate. So this is how you can create your app from the app designer. Okay, similarly, and there is another example is the filter designer. So filter designer is basically one app which is very much helpful. So here you can see that from here you can see the response type. Okay, response type. Suppose if you click on the filter designer app, or if you write the write the command, that is the filter designer. This is the filter designer, but it is in the camel case. It is in camel case condition. Okay, so filter, but D is capital, ESIGNER, filter designer. Okay, so like that way you can create, you can open the app. Okay, next is the, okay, it is opening from my end. Okay, now next there is an option that is the low pass, high pass, band pass, low pass, high pass, Nyquist, inverse sync. Okay, so this is the response type of the filter. Okay, now next thing is the, here you can see that um, uh, band stop. So if I consider the band stop, so there are different options, that peaking, hybrid transformer, multi-band. So there are different options are there. Okay, okay, so now the design method, you can select which type of design method you want to use, like IIR, infinite impulse response, or FIR, finite impulse response. So if you click on the IIR or FIR, suppose I am clicking here the FIR, you can see the different options like least square method, or maybe window method, or interpolated FIR, so etc. So this is basically the design method for FIR. Okay, so you can see the equi-ripple design method for FIR filter. Okay, and for IIR you can select like Butterworth, Shazek filter. So this is basically the, now next thing is that here you can change the order. You can specify the order. You can select the frequency also change the magnitude and the bandwidth. Okay, so here you can see the your filter order. Okay, so here you can write 10 is the your order. Okay, and after that you can pass band frequency or stop band frequency, as well as the sampling frequency. You have to mention the sampling frequency value, pass band frequency value, and the stop band frequency value. Okay, so like that way you can put your um, put your value. Okay, here next. Okay, this is the omega is basically called the angular frequency. Okay, angular frequency, omega is the angular frequency, that is in radian per second. Okay, so you can put the angular passband frequency, angular stop band frequency. Okay, now the units, the magnitude specification, while magnitude specification generally you want try to select in dB, that is in decibel. And A is basically the amplitude. Okay, for pass band, and for stop band you can mention the amplitude here. And finally you can, if you click, and just a minute, if you click here, you can see the pass band 0.2. If I consider that 0.2 is a pass band, so here 0.2 is my pass band. Okay, and after that you can find the stop band frequency at 0.3. So so it will stop at 0.3. Okay, so it is represented in omega. Okay, so you can see that the frequency at omega, that is the 2 pi f. Okay, 2 pi f. So normalized frequency into pi radian per samples. Okay, so this is how you can select the create the magnitude response of your particular filter. Similarly, if you want to change the uh, frequency, okay, passband frequency or stop band frequency, okay, so like that way you can see that passband frequency at 2 and stop band frequency at 3. Okay, so you can see the structure of it. Okay, and after that, after generating the that kind of waveform, you can, if you want to generate any code, so there is an option to generate the code. Okay, so like that way you can create the IIR filter or the FIR filter, so like that way. And here you can see, so this is how you can generate the waveform. Okay, just a minute. Yes, this is my MATLAB window. So I think it is visible from here. Okay, just a minute, because because the time is really short to explain that thing. Okay, so if you select from here, okay, so this is suppose mm, your your design. Okay, your design, and after that you can store your filter here. Okay, store your filter. Okay, so from here you can select, just a minute, you can store your filter in the filter manager. Okay, and if you want to deploy it, just a minute, just a minute. So you can store your filter. Okay, and if you want to export any Simulink model from here, so you can click on the Simulink model, or you can import in the filter in the workspace also. And also just a minute, yes, there is an option to suppose I already have told you that how to deploy the code to your hardware. There is an option to generate HDL code, that is a high definition language code. So if you want to use any Xilinx board, okay, so uh, you can generate the C code or the HDL code for it. Okay, similarly, you will get different types of response like phase response, phase delay, impulse response, step response, pole zero plot, etc. So from here, so for particular filter, you can get the magnitude and phase response, and after that other parameters like impulse response or step response of this filter or pole zero plot, that kind of information you will get from here. Okay, and another important thing, yes, there, that one, so that is the basically the generate MATLAB code. Okay, so if you design any filter, hello, my voice is audible, na, sir? Hello, sir, my voice is audible? Yes. Okay, thank you, sir. So if you generate any filter here, so then after simulation, okay, either you can export the Simulink model, okay, so in block diagram based form, or you can generate the filter, because I can run this Simulink model, but if I run this, then the system will uh, may hang at that time. Okay, so right now as the PPT and all the I mean the several windows are open, so that's why just you can follow that step. You can at your convenient time you can try it. Okay, so after that, suppose from that app, okay, you can generate the MATLAB function. Okay, so there is no need to write any specific code. Okay, so just you can generate the filter design function, and after that you can deploy it to your system. Okay, so yes, this is the way. So you can select the units at hertz or kilohertz. After that, here from here you can select you specify your order. Already that video, in that video I have already discussed that thing. So you can select that order. You can here, this is the differentiator. Okay, so you can multi-band. Okay, so you can, from here you can see the multi-band or the differentiator, or so different options are there. Hilbert transformer, so there are different options that you can select. Similarly, in response type you can see that uh, Nyquist response, or maybe for the, just a minute. Hmm. So like that way you can change the value. Okay, change the options. Okay, and after that, okay, I like that way you can change it. Okay, you can change these options. Okay, you can change a multi-band or something else, like that way. And if I this is equi-repeal. Similarly, you can change the least square. So there is a options that are available here. Okay, so if you click on the design filter, if you click on the design filter, on that basis, on that response type, or if you select the first order or other type of frequency or magnitude specification, the filter will be designed. So filter will be designed, and after that you can store it. You can store it to your uh, sys- uh, 1 minute. Okay, it will take time. Okay, just I am moving to the this part. So here you can see, that yes, there is a different options you can see. So you can store it by store filter or filter manager. Okay, similarly, you can see the different types of response. Already I have told you that there is an option that is called the magnitude response, phase response, step response, impulse response, frequency response, phase delay response. So here you can see the different options. So here, from here you can see, so these are the option. While yes, here you can see the filter has been designed. Here the filter has been designed. Now you can, this is the magnitude response. Now you can click on the phase response. Okay, yes, is it visible? So it is the phase response. Next you can check the phase delay response. So phase delay response, or maybe the impulse response. Okay, so have you understood that one? So this is easy, very easy. You can use the filter designer app. You can select from here. You can go to the MATLAB section, get MATLAB section, go to this one, that is the filter designer app. 1 minute. So this is the filter designer app. Filter builder, filter designer, these two apps are very important. Okay, but I am just showing here now filter designer app. So it is very much helpful for you. Okay, uh, and after that, sorry, and after that you can see that, suppose pole zero plot. Okay, so you can check the pole zero plot, and whatever be your code. Yes, yeah, you can generate the code from here. So if you click on it, okay, filter designer function, if you click on the filter design function, then you can generate the function from here. Okay, similarly you can generate the code from here. I am showing you. Yes, so you can save this file in the .m format. I am not saving for now, but you can save the file in the .m format. Okay, 1 minute. Yes. Now another important thing is that in this simulating platform, this is the filter designer, where you can see that this is basically my transfer function. If I consider the z transformation, okay, z transformation, then it can be represented like that way. One is the numerator, another is called the denominator. Okay, so after that you can see that is represented in this closed loop format. Okay, so these are basically the um, um, error detector. Okay, you can see the summing amplifier, or you can see as a error detector. Okay, this is the gain block, and this is the z transformation block. Okay, z transformation block. So uh, here you can write, so -7/4 into z of -1. So you can use the 1 by z block here, and -7/4. So this is the sum block. You can use the sum block by summing amplifier block. If you want to change the plus minus value, so from here, if I want to change the plus value or the minus value, so if I write plus and minus, then here it is written the plus and minus. If I write here minus minus, then it is written here minus minus. Okay, so this is the sum block. It can be acts as a add block or the subtract block. So the signal coming from this input port, one input port, is reached to here. Another signal is coming from this summing block is reached to here. Okay, so if I want to represent that filter, then I have to write like that way. So it is 1 -7/4 into Z1, because this is at these two blocks are at cascade condition. Okay, cascade condition. So it is in series. So definitely these two blocks, this is the delay block. Okay, so and this is the gain block. So -7/4 into z to the power of -1. Okay, similarly these two blocks will be added. Okay, -1/2 into z to the power -2. Okay, now the sign is, so if you consider here, within bracket, -7/4 into z1 plus 1 by into z2. So as it is minus here is written already, minus is written here, so no need to change anything. So here -7/4 into z1 means plus, -1/2 into z2 means plus. So here it is written plus plus, and if it is here 7/4 and 1/2, then you can write here minus and minus. Okay, so like that way you can write. Okay, so 1 -7/4 into z1, and these two are in parallel because this is the two blocks which are connected in parallel. Okay, and after that you can add these blocks like that way. Similarly from here it is represented the numerator block. Similarly it will represent the denominator block. Okay, like that way. And like that way you can design the filter by after z transformation. Okay, so if you run the program, you can get the output. 1 minute. Yes. Okay. So let's give some time to compile it. Okay. In between, I am just showing you. So this is basically how you can. I think you have understood how you can design. We can design the digital filter and evaluate the magnitude response, phase delay, pole zero pot, etc. So this is done by the MATLAB apps. So I think I have discussed that how you can use the digital filter. I mean how you can change the filter parameter and visualize the different filter characteristics. So and how you can generate the code. Already I have told you that how we can generate the MATLAB script from this filter designer app. So yes, so this is the filter designer app. You can find in the app section, and also you can you can design this type of digital filter in the Simulink platform, because this is basically the Simulink platform. Here you can change the block parameters and you can get the result. Okay, another important thing is that if you go to the model setting, it is very important. Suppose if you are interested in hardware application. Hardware means Xilinx, Altera board, FPGA board, ARM Cortex. So these are basically different types of hardwares. Okay, so here to reach to the hardware, first you need to install the hardware support package. How to download the hardware support package? Go to the home section, go to the add-ons option, add-ons. Here you will find the get hardware and support packages. You click on the get hardware and support packages, and if you click on it, then a window will open where you will find the different hardwares uh, that can be interfaced only with MATLAB. Suppose you are using Raspberry Pi 4B plus, but if there is another model, and the package of Raspberry Pi 4B plus is included in the MathWorks site. But if there is another series of Raspberry Pi, and if you want to interface with the MATLAB software, it might create problem at the time of hardware interfacing, because the different series may not be interfaced with the software platform. Okay, so here you can see that different types of hardwares. It is a little complicated because hardware interfacing is really challenging. So before that, you need to install these kind of hardware support packages, because Arduino, Raspberry Pi, or suppose in case of image processing, camera is required, or these are basically for the embedded coder support package for ARM Cortex processor. Already I have told you that one challenge where we can deploy the code in the ARM Cortex processor. So at that point of time, you need to install. If you click on it, you can see that already I have installed that one. Otherwise, there is an option that is called install option. Before that, you need to create the MathWorks account. I think Dr. Shalu Madam has discussed how to create the MathWorks account. Okay, and you first create the MathWorks account, and then only you can able to download and install this support package to your local computer. Otherwise, it will cannot be possible to interface the hardware with this MATLAB software platform. Okay, so this is important thing, it is very much important. Okay, and yes, there should be the compatibility that is also mentioned, and here you can find the relevant codes also. Okay, and how to download, how to install uh, the, that kind of documentations are there. Okay, so yes, so this kind of hardware support package you can download and install for signal processing application. So there is a application area that is called the signal processing. Okay, signal processing, and here you can see for signal processing application, Arduino, Raspberry Pi, or antenna, some communication toolbox like Xilinx ZYNQ based radio support package, or mic. Okay, so the hardware from the Keysight, uh, hardware from the National Instrument NI. So these are the available hardware support package. If you want to if you want to use another series of, suppose, ARM Cortex processor, it might not be uh, accessible. Okay, so this is one thing. And another important thing is that after that, you can, after installing the hardware support package, there is a list of instruction. So if you go to the MATLAB documentation page, just a minute. Oof. Oh. If you go to the MATLAB documentation page, there you will find the how to install the Raspberry Pi, or what is the basic function and the program. So this is the MATLAB documentation page. Okay, you can follow, definitely you will follow this MathWorks documentation page. Here you will find the relevant examples, and suppose you are using the signal processing toolbox, only the signal processing toolbox. So in this signal processing toolbox, what are the relevant functions? Okay, so and also you will find the which functions is used for which application, and the descriptions of this particular inbuilt function. So this can be well documented here in this site. Okay, just a minute. Yes, so this is, I think it is visible. So go to the documentation home, go to the documentation home. Just a minute, hold on. Go to signal processing part, and here you will find the DSP tool, system toolbox. Okay, so you will get the documentation of how to generate the signal, how to design the filter, FIR filter, and so on. And AI for DSP, I am not I will discuss little bit the AI of DSP, that is the advanced applications of DSP. Okay, and but here suppose I am working on the Raspberry Pi. Okay, so here you can see that how to connect the board. Suppose I want to connect the Raspberry Pi board. Okay, so there is a particular command, that is the RASPi. RASPi is particularly the command to create the connections with the MATLAB software. Okay, I have already done it. Okay, so but before that you need to install the Raspbian OS to the SD card. Okay, so similarly you will get the functions. Okay, different functions for Raspberry Pi applications. So similar type of functions you will avail in MATLAB. Okay, okay. Next thing is that now I am talking about the hardware. So this is if you go to the, again I am showing you, if you go to the Simulink, this is the Simulink platform for the model based design. This is the Simulink platform for model based design. Okay, so if you open any blank Simulink model, so from the Simulink library browser there is a simulation. If you click on the library browser, if you click on the library browser, then Simulink library browser will open, and from here you can drag and drop these blocks. Next is the modeling. So if you click on the modeling, go to the model settings, click on the model settings. If you click on the model setting, then configuration parameters, this type of window will open. Okay, go to the hardware implementation, and here you will see the list of, just a minute. Yes, so here you will see the device vendor. Okay, so basically here you can see the Texas Instrument, Intel, AMD, Altera, STM Electronics. So these are the different device vendors you can find from here. Okay, similarly here you can see the hardware board. Okay, Arduino Uno, Arduino Nano, Arduino Mega, STM Electronics, instruments from the Texas Instrument, Xilinx board. So there is a series of Xilinx ZYNQ board. Okay, so there are different series you can see. Okay, but if other series is there, okay, you may not connect, you may face problem to at the time of connection. Okay, so and if you want to code generation, so there should be some coder that is called the MATLAB coder, or MATLAB coder, HDL coder, embedded coder, Simulink coder. So these coders are helpful to generate the C++ or HDL code. Okay, so here you can see that if you want to generate the language, suppose this is my Simulink model. So from this Simulink model, I want to generate the C++ code, and you can directly deploy it to your Simulink model, directly deploy to the hardware. Also you can generate the C++ code from this Simulink model. So this can be done very easily by selecting the C++ code. Okay, okay. So this is the example of the filter design. That's 1 minute. Okay. So another example is that. So another example here. Just I am time is less. Uh, okay. So simple things. What we have done in apps, that kind of same thing we can write in the MATLAB script. So you have to assign the passband frequency, you have to assign the stopband frequency, also the amplitude or amplitude of the passband and the stopband. And if you want to design the filter, then you have to write the design FILT. This is the built-in function, and you have to pass the parameter here. And finally you can get the magnitude response from here by using the FB tool. So here you can see this we have done. I have done here the minimum order FIR design. So FIR design. So here, if you want to design the minimum order FIR filter with the passband frequency of 0.37 pi radian per sample, and the stop band frequency 0.43 pi radian per sample. So here I have mentioned the passband and the stop band frequency. Okay. And also I have mentioned here the passband ripple of the 1 dB and stop band of the attenuations of the 30 dB. Okay. Okay, so like that way. So if you want to assign the order, okay, or if you want to resulting the filter order, that so you have to use the filter ORD function. Okay, so to get the filter order, and you can get the informations of it. Okay, of design the filter. So what is the stop band attenuation, pass band attenuation, ripple, okay, and etc. So this can be done very easily by using this script. Okay. So this is more or less same. You can find the magnitude response, phase response, etc. from this different types of filter. Okay. Just a minute. Hold on. Okay. I am just explaining one, two, or yes, 1 minute. Filter, yes. Okay. one- oh, okay. So just I am showing you the convolution. Okay, so basically here we have talked about the digital filter. Now what is convolution? Convolution is basically the fundamental operation of the DSP, digital signal processing, and it is basically the mathematical operation that actually combines two functions. Convolution means more or less like digital I mean the multiplication. It is almost similar to the multiplication. Okay, so it is basically combines the two functions that actually produce a third function. Okay, so in this context of DSP, there are two typical signals like HK and XK. So XK is basically the input signal, which is basically convolved with the impulse response. That is basically the HK. Okay, so impulse response is HK and the input is XK. So I want to create another typical signal, that is YK. So YK is the output. So YK is the HK into XK. So that is the summation of T 0 to equal to minus infinity to infinity HK of minus L XL. So here I can use the same way. That is the first I have assigned the time frame, like my lower limit and upper limit, and also the step size. Okay, and after that here I am using the tripulse. Okay, tripulse for for particular function like trigonometric function, and after that or after that you can convolve the triples with the other triples. Okay, so here you can see that this is the two functions xk and hk, that while it is convolved, this is one signal, this is another signal, so these two are multiplied with each other and create another type of signal. So this is basically this tripole signal basically helps to generate the triangular waveform. Okay, so if you want to generate the triangular waveform, first you can mention the time t1, and here t1 comma 2 means two type of triples can be generated, and it will be plotted in the two subplot. And after that, if I want to convolve the two trigonometric signal which is generated from the triples function. Okay, so I can use the conv is the for the convolution purposes, and after that we can plot it and get the plot like Gaussian pulse. So like that way, yeah, I can do the convolution. Similarly, if I want to uh, do other type of convolutions, that can be also possible, like for if I want to create any step signal, or if I want to shift any kind of, if I want to work with the shifted signal. Okay, so that can be possible in to the convolutions techniques. Okay, uh, 1 minute. So I think it is easy that how to design the filter, Lucas filter. It is discrete Fourier transform. Uh, okay. Um, okay, I think more or less it is discussed. Okay. Yes. So this is one example. Just I am showing you that one. So it is FIR and IIR filter. Okay. So what is basically, while we are talking about the digital filter, the digital filter basically divide in two part. One is the finite impulse response filter. Another is the infinite impulse response filter. So in case of finite impulse response filter, basically output depends only on the current and the previous input samples. Okay, but in case of IIR filter, basically output depends on the both current and the previous input samples as well as the previous output samples. Okay, so here you can see that it provides the impulse response for a finite durations of time, uh, but in case of infinite impulse response, it will provide the infinite impulse response infinite durations of time. The feedback is not present here, but in case of infinite impulse response, feedback is present. The nature is non-recursive, but nature is recursive. But here you can see the stability is more due to the absence of poles, but here stability is less due to the presence of poles. Okay, computational efficiency is less, here computational efficiency is more. So in case of FIR filter, already I have told you that differentiator, Hilbert transformer, Hilbert transformer. So these are basically the FIR filter. In case of FIR filter, these are the basically the types: Chase filter, Chebyshev filter, or the Butterworth filter. These are basically the IIR filter. So now this is basically the example in Simulink platform. So just a minute. Okay, I think it is visible. Uh, okay. Yeah. So here I can create the chop function. Already I have told you that how to create the chop function, CHIRP chop. We can create the linear chop functions or the quadratic chop function. If we want to generate the sweep frequency waveform, So at that time we can use the chirp function. So here lin chirp stands for the linear chirp function. Okay, now here two types of filter that can be used here. Okay, one is the IIR filter, another is called the FIR filter. Though it is represented here in that way, but it is basically that represented in the form of subsystem. Okay, now here to this is the output response of the filter is represented in scope. So this is the output of the FIR filter. This is the output of the 1 minute. This is the output of the FIR filter, and this is the output of the IIR filter. This is represented in scope. Okay. So in case of time domain, you can see that kind of output. In case of frequency domain, you can see that kind of output. Okay. So I will try to show you possible. Okay, it will take some time. Okay, let me discuss other two things, two or three things. So basically here you can uh, uh, design any FIR filter and a IIR filter. There is a certain block, okay, which having some subsystem. Okay, so if you open the Simulink window, okay, there is already inbuilt app is there. Or yes, or I can show you from here also. FIR filter, 1 minute. FIR filter, if I consider here FIR filter, okay, I'll show you because my computer is not responding. Okay. So this is this type of examples you can see from here. Okay. So though it is written in FIR filter in Simulink, if I type here FIR filter in Simulink, you can see that type of block diagram. I think if it is available here. Okay, so that kind of documentation you will get from here. Okay, so design filtering design and implementation in Simulink platform. So you can just type and type here. You can see some basic example. Okay, I think 1 minute. Okay, so okay, participants, you can see from here, you can see that different FIR blocks and IIR blocks. Already I have told you that if you want to create any you want to create any frequency response of FIR filter, so there is a certain block, IIR filter block or the FIR filter block in the Simulink platform. Here you will find out some blocks for the under digital signal processing toolbox. Okay, so this is the basically the Simulink diagram. Okay, Simulink diagram or the Simulink model. So you can create the linear chirp functions, you can use the converter block. Okay, and after that there is a block for the FIR filter, and you can see the response of the FIR filter in the scope. Here you can find the output in the scope. So this is connected to here, so you can visualize the input response of the linear chirp function, or input waveform the linear chirp functions, and here from here you can see the response of the FIR filter as output. Okay, so that can be done in the Simulink platform. That can be done in the Simulink platform. Okay. Okay, so if you open the library browser, just I am showing you. If it is possible, then I can show you. So if you open the library browser, so library browser is there where you can find the different toolboxes, also the relevant blocks under this particular toolbox. Okay, so you can click on the library browser, and if you go to the DSP, that is called the digital signal processing toolbox, then you will get that kind of blocks. Okay. Okay, I am skipping that one. I want to show you some one important. Uh, so this is the example. So if you want to use that kind of hardware, okay, you can create the model in the Simulink platform. Okay, create the model. So this is the model. Okay, so you can create the model, uh, and after that you can deploy it to the hardware. So you can generate the HDL code and you can deploy the code to the this FPGA board. Okay, I'm not. Next, advanced application is, if I talking about the advanced application part, I can I can uh, I can say that the CNN, that is the convolution neural network, or the deep learning, is basically the advanced part of the signal processing. So basically what is happening here, how does it work? Already yesterday in the deep learning session, ma'am has already mentioned that basically deep learning is the subset of machine learning, subset or subfield of machine learning, where multi-layer neural network is there, and it is basically the end-to-end solutions. While you process any image, process any signal, it will create a probabilistic score or probabilistic outcome directly while it is processed through the hidden layers. So here you can see that if it is considered as input layer, this is called hidden layer, and if it is the output layer, okay. So the input is processed, and after that it will reach to the output layer, and within this hidden layer the feature extractions and classifications can be done. Okay, so this is the convolution layer. If I am talking about it is a signal, so then it is convolved with the other signal, and after that it will create uh, another matrix or another feature map, and after that it will after processing to the fully connected layer, it will go to the gives rise to the probabilistic score. Okay, so this is basically the input layer, hidden layers, and output layer. So it will work on image as well as on the signals. So here you can see, suppose it is an image. So there is a three layers are there: convolution layer, ReLU is the rectified linear unit layer, pooling, and also the pooling layer. So while any particular filter, or you can say this as a kernel, while work on the particular matrix, or while it is convolved with that matrix, it will create a feature map, and after that by ignoring the negative value, or extracting the maximum or the average value from that particular matrix, it will create a feature map. So like that way, this is done in the hidden layer, and after that there is a layer that is called the fully connected layer, and classification can be done with a certain probabilistic score. So here you can see that if I talking about the sound type classification, so if we use any particular type of network, okay, deep learning, deep neural network, so this will work on the sound type classification, basically for the voice recognition. So um, it is a gunfire sound, or it is a sound of a dog and animal, or the domestic animal. So these kind of classifications can be done by using the sound type classification. So here, in case of this type of advanced deep learning uh, algorithm or deep learning model is there, which will work on the input signal, okay, which will work on the input signal, and it will finally find out the which sound it is. So this is basically the signal processing engine, okay. So where this is processed through the input node, then it will reach to the hidden layer, and after that it will reach to the output node, okay. So basically the model will work on it to classify the sound. So here YAMNet, like ma'am has already told you, the AlexNet, GoogleNet, ResNet. So these are basically the network, deep neural network. Similarly, YAMNet is there, basically used for the classify the sound of the different different a model, okay. So here this YAMNet is basically trained with the thousand of hours of annotated audio from YouTube videos, and 521 different semantic classes are there, okay. So there are 520 one of different classes are there, and thousands hours of annotated videos from the YouTube videos. So it will be trained with that data set, okay, train with the data set. And after that, here you can see that if you want to classify the sound, so you just call that network like net equal to either you can write net equal to YAMNet, and after that you can write classify sound. Then whatever be the sound, if it is stored in a particular variable, so then it will create the graph, okay. So that kind of YAMNet graph can be generated, okay. So here you can see that feature extraction or the time frequency transformations can be done here, okay. uh, okay. Okay. So another important thing is that suppose you have a signal file. Okay. Suppose you have a list of you have a MP3 file or the MP4 files. Okay. So you can store it. You can store it to the um, folder. Okay, so and you can bring that CD data folder. CD data folder means if you want to access the whole folder, you can write the CD data folder. So whatever be your file, that this is the MP3 file, you can first you have download from the data repository, and then you can put that audio signal or the audio to a particular folder. Next, here you can see that full file. Full file is basically, suppose you want to access whole MP3, okay, yeah, at a time, okay, because your objective is to process the whole MP3 at a time. So at that time, if you want to access it, because at initial you have to train it with your audio signal. So to access the whole folder, if you have to use that command, that is the full file command. Next, this is the URL. From that URL, you would directly download the Google zip. So like that way you can download, because this is your data repository. From the data repository you can directly download the Google speech, and after that the download folder is here, and then process the download folder, as a data folder. Okay, so to access all the mp3 file or the audio file, you have to write the full file. Now here you can see that unzip is basically to unzip the folder that is present in this site. You can directly download and unzip the folder here by using this command. Okay, and just a minute. And after that you can store the data in this format. Okay. Mm. Okay, so you can store the audio from the data folder, so audio data store, like that way. And after that you can, this is the for the training purposes. Okay, so you can train with your data. And here you can see that if you this audio store is this is written, this is stored in this variable ads. So if you type ads in the command window, then you can see the properties of the audio data store with the file names. Okay, so you can see the labels, you can see the files, etc., etc. Okay, so next thing is that yes, so here you can see the different types of categorical data. Okay, so categorical data, so you can see from here categorical data. And
Mr. Majumdar,
yes.
I'm sorry to interrupt. We're just running a bit short of time,
Yes,
as
yes, yes.
yeah, we also have a meeting schedule. So we can please wind up the session quickly.
Okay, okay, okay. So participants, I think I mean the signal processing is a vast thing, so it is not possible uh, to cover all these things in the 2-hour session. So, but here I think I am trying to give you the idea. Okay, so basically, what are the functions and what are the resources? I recommend you to follow this first. If you are really interested to work on the hardware or the real-time based applications, you can download the hardware support package from this website, MathWorks site. Okay, you can create your MathWorks account by sign in, and after that you can able to download the hardware support package for hardware based applications. This is one thing. And another my suggestion is that you can visit the MATLAB documentation page, because MATLAB, if you go to the MATLAB documentation page, there is an option that is called documentation home. Okay, you can see the product list, and you can see that product list, and here you can see the DSP, because our topic is DSP, so digital signal processing toolbox is important. So here you can see the AI for DSP. Suppose wavelet scattering, I have missed the wavelet scattering. Okay, so waveless scattering is also important. Similarly, code generation is also important. And next is the DSP system toolbox for supported hardware. So you can see that different types of examples you can see from here. Okay, and yes, here you can find out the examples you can open in the MATLAB online platform. Okay, how to design the low pass FIR filter, IIR filter, etc. Time delay and scaling of the multi-rate DSP filter. Its functions, because whatever uh, I mean the script, you can find the functions. Okay, so if it is a filter designer, so I have shown you the filter designer app, how to work with the filter designer app. So what is the command? The filter designer is the command. So what is its description? It is the description. So to open the filter designer app, you have to write the filter designer app like this way. So this is the list of I mean the tools, list of functions that you can find from here. Similarly, the blocks which are available, also what are the apps are there, because for filter designer or other option filter analysis you can see here, and also what are the relevant apps that you can find out from here. So I would like to suggest that this is the important app, and you can follow this documentation page for your future. Thank you.
Thank you so much, sir, for this wonderful session. And yes, digital processing is obviously not a topic to be summarized in 2 hours, but I think you've done your best so far. If this participants have any queries, you can drop in the chat box. If you have any queries, you can please ask. You can also reach to Mr. Majumdar probably on LinkedIn, and if you have any questions related, you can ask him. So on behalf of the organizing committee, I would like to thank you once again, sir, for joining here with us, for taking out time from your busy schedule, and for addressing the gathering. Thank you so much.
Okay, madam. Thank you so much.
Participants, we will meet again tomorrow at the same time, that is 2 p.m. And requesting you all to please join in time for tomorrow's session. Thank you and have a wonderful day.
Thank you, madam. Thank you.